Hello everyone, my name is Kendo Matayo. I'm a graduate student at Tensegrity University, and the name of my graduate advisor is Dr. Raganatha Patasarati, and I'll be talking on design of Tensegrity structures for phase transformation leading to energy dissipation. So before we proceed, let's look at the definition of Tensegrity structures. Tensegrity is a short form of tensional integrity. They have continuous compression member inside a tension chain or sea of tension. In structural engineering, the most common tensegrity structures are the tensegrity trusses, such as this one in Kansas City. But tensegrity structures are found at many different scales. For example, the cytoskeleton of living cells has been proved to be a tensegrity by Donald Eber at Harvard. Some tensegrity structures have a particular feature that make them have multiple stable configuration. These phenomena give high energy efficiency to mobile or moving structure. For example, we know that walking is a highly energy efficient mode of locomotion for humans. The archie tendon store energy and release energy with each step so that we fall forward with each step, making walking very energy efficient. We can realize such energy efficiency in another moving structure, taking advantage of transition between different stable configuration of tensegrity structures. Here, this is a communication tower that was damaged in a storm. In the bottom, here is a concept of tensegrity communication tower. When the load exceeds a critical load, it flips to a new configuration rather than getting damaged. After the storm, the tower can be giving some stimulus. This stimulus could be in form of electricity or external forces, and this brings it back to the original configuration. Basically, we're achieving some form of dissipation where the energy is at the structural level instead of the material level, and so it can be restored. So our motivation here is to investigate whether there is a systematic procedure to come up with tensegrity structures that have multiple stable configuration along with the force deformation behavior associated with the structural phase changes between different stable configuration. Currently, researchers are still using an empirical or semi-empirical method for this purpose. So our motivation here is a simplest tensegrity structure, which is the simplest 3D tensegrity. It has 3 compression members and 6 tension members. As we can see here, none of the compression members are touching each other. As we see in the video, the structure switches to a new configuration when it is compressed, nearly all the way to the bottom. We made this at Tennessee State University, and this motivated us to try to come up with simulation that can capture this behavior. Our objective include develop an algorithm for form finding, to demonstrate phase change using physical model, to develop a procedure to model change structural phase change in example 3D tensegrity. As we see in the video, design tensegrity structures have extremely high geometric nonlinearity, although there may be no material nonlinearity. Therefore, a force-based approach, which is more used traditionally in structural analysis, becomes difficult because an energy-based approach is easier since the geometry can be obtained simply as a solution to the problem of minimizing the potential energy. For simplicity, in this research, we consider the strut as incompressible and the tension member or cables as a linear elastic material. Therefore, the potential energy only involves the stretching of the cables. They are assumed not to be able to carry any compression and buckle immediately. So what is form finding? Form finding is the process of determining the initial unloaded geometry of the tensegrity structure. The only information that we need are the original length of the cables and the elastic modulus of the cable. The form of the loaded structure is found simply by minimizing its potential energy. This is another popular example of tensegrity, which is icosahedron. We can see here all the developed connectivities. The yellow numbers here represent the tension members. The black numbers here represent the compression member, while the red are the node or the joint itself. This is also an example of fault finding result from the simplest. In the dotted figure, we can see our initial approximation of the simplest, which we took to be a prism. Once we run through a form finding form, minimize the potential energy, it goes to a twisted prism, which is the correct equilibrium geometry. As we can see, this matched the physical model which was made at Tennessee State University. Here is also another example which we currently predict the equilibrium geometry. In this case, even if the initial estimate of the geometry is way off, the algorithm is still robust enough to convert to stable configuration. So here, in order to simulate the physical compression test, the base of the simplex is constrained to V is equal to 0, and the top of the simplex is displayed downward by incrementally reduce the Z for each increment. The potential energy is minimized since we assume quastatic deformation. In the plane as well as the bottom, the X and Y coordinate can be freely adjusted to minimize the potential energy. The member lengths are proportionally equivalent to the physical model, but the absolute value are arbitrarily chosen. When all the three nodes from the top plane display equally, we find that the structure does not undergo any phase transformation, but actually it reaches potential energy maximum at the very bottom. Then as we see, the left-hand side show the simplest is getting compressed, and the right-hand side show the potential energy is maximized at the bottom. The shape of the potential curve are not on the absolute value since the simplement of the tension member are arbitrary. In this simulation, only two of the top nodes are displaced downward, and the left top one is free. Similarly, the two bottom nodes corresponding to the strut being displayed are constrained to the Z is equal to 0 plane. The bottom node of the free strut is free to lose contact with the Z is equal to 0 plane. We can see that in this simulation, the potential energy reached a maximum and experienced a dip. This dip corresponds to the phase transformation that we see both in the simulation as well as in the physical experiment. Here, when one of the vertical has a slightly smaller initial length, we observe that this simulation show phase transition, which is almost identical to what we observe in the physical experiment. At the point when the phase transition happens, we can observe that the potential energy suddenly drops as the structure moves toward the horizontal stable configuration. From the graph, we see that when the stretched length of the shorter vertical cable decreases, the phase transformation happens earlier under the compression. As this video shows, we can confirm this from the physical experiment. We observe a dramatic shift in behavior when the length of the shorter vertical cable is about 33% shorter than the rest of the cable. Here, we show how the ability to predict the phase transition can be used to design moving structure or impart dissipating structures. For example, lattice structures are composed of simplex units, could be designed to undergo phase transition throughout its volume at a specific load. We can use this concept to engineer the Tensegrity communication tower, which we showed earlier in the beginning. Another application of this is that it could be used to reduce the energy required for actuation in moving structure. For example, the bridges that is shown here is an open bridge, like the one that let the ship go through. Only some initial covering of the bridge will need external energy supply, and phase transition will drive the bridge through the remainder of the path. And similarly, for the closing of the bridge. In conclusion, a robust algorithm and MATLAB code have been designed for fault finding of Tensegrity structure. The phase transformation of the simplest Tensegrity has been demonstrated using both physical experiment and numerical simulation. This phenomenon can be leveraged to improve efficiency of actuation mechanisms in moving structure and to design impact dissipating Tensegrity-based lattice structures. Our future objective includes fault finding from simplex Tensegrity through understanding of simplex unloading behavior, study of structural phase transition in other Tensegrities, and lastly, study phase transition in modular Tensegrity, linear like 3D or 2D. So this is my colleague Ami sitting on the Tensegrity table. This shows that the Tensegrity, when it is fully made, it has the strength, it has the capacity, and it has the rigidity to take any load being put in on it. So at this point, I would like to acknowledge Dr. Animizra at the University of Kansas, Dr. Lin Ki from Tennessee State University, and Dr. Abiodun Fasho from Tennessee State University. Thank you so much. We appreciate it.